Hey guys, welcome back to Calculus Universalis, and today we're going to be going over 1.2 computing limits for AP Calculus. So, let's get started. We're going to compute limits today. So, computing limits is evaluating a limit by plugging in the x value which it's going to. So, for example, if I have this problem, limit as x goes to 1 of x to the 7th minus 2x to the 5th plus 1 to the 35th power, how are we supposed to evaluate this? This is a huge inner function, and it's just unbearable at the moment. So in order to solve this limit, what we're going to do is this. Plug in a 1. So we're going to have the limit as x goes to 1, plug in the 1, minus 2 times 1 to the 5th plus 1 to the 35th equals, right? This is going to be a constant now, so we don't have to have the limit notation anymore. We can get rid of this and just write it as a number. So it's going to be 1 minus 2 plus 1 to the 35th, which is going to be 0 to the 35th, which is 0. So that's our answer for this limit. And it makes it much more easier when we can just plug this in. But as you're going to see down below, this gets pretty nasty quickly. What if we have a one-sided limit? You might be used to limits where the function is continuous. So if I have a limit and I want to evaluate it at this point, and I see, oh, well, this is 2 y value and this is 0 for the x value, so it's going to be as x approaches 0, it's going to be 2, right? But what if we have a function like this? We have our axis, our x and our y, and this is our function. Then what? So if we want to evaluate the same limit as x goes to 0 of this function f of x, how are we supposed to figure this out? Because they're two different things. And if we're approaching it from the same side, just from like the center, not approaching it from the left nor the right, we're just approaching it from both sides, we're going to get an x equals 3, or y equals 3, and a y equals, let's say, 1. These are two different outputs, and then we're going to have a 1, which doesn't make sense. You can't have two of them outputting two different numbers. So, to fix this, well, it doesn't even fix it really. This limit just simply does not exist. It does not exist. You cannot evaluate something when it has two different y values. So, in these problems, it's either going to be does not exist, or they'll give you something like this, approaches 0 from the right. And then what? You want to see what y is doing as it approaches from this side, the right. And what's it doing? It's going to 1 for a y value, so this is going to be 1. But what if it said from the left? It's going to be 3, because it's coming in from this side. So this is going to equal 3. And these are the things you have to look out for, because not every limit is going to exist. There's going to be tons of times where, the denominator is 0, and you just simply cannot simplify it to get a value, so it's just going to be DNE, does not exist. So you're going to have to look out for that stuff. So, an example of this, looking out, is going to be the conjugate theorem. We're going to have nasty limits that look like this. Limit as x goes to 1 of x minus 1 over root x minus 1. And if we're going to plug in from the computing limits idea that we just learned, if we plug in a 1, it's going to be 1 minus 1 over root 1 minus 1, which becomes 0 over 0, which is indeterminate. It's an indeterminate form. This is a big no. You cannot get something that is an indeterminate form. You may get something that just simply does not exist, right? And that's going to be your answer. You can put this, but you cannot put indeterminable. You're going to have to put does not exist. But for this one, it's not indeterminable. In this form it is, so it's an indeterminate form. But we have to fix this. So we're going to use, you may see problems where you can just simply cancel out something and it'll work. But in this circumstance, we're going to have to use the conjugate. If you don't remember, the conjugate is applied when we have something like a square root or a cubic root, usually just a square root, because they cancel each other when multiplied. So the conjugate of this is going to be root x plus 1 over root x plus 1. It is the same thing as this, but we're going to add a plus and multiply because this is going to cancel out very nicely. So if we multiply the top together, we're going to get limit as x goes to 1 of, multiply the top, let's just keep it in factored form, root x plus 1 divided by, multiply these two, and we can do the FOIL method, but in the end you just have to memorize that these are going to cancel. You're just going to be left with x, and then these are going to be multiplied by each other, but you're going to keep this sign, so it's going to be minus 1 still. And look how perfect this is. We can cancel the minus 1s. Scroll down here, and we're going to get limit as x goes to 1 of root x plus 1, and now we can finally plug in our value to get root 1 plus 1, which equals 2, and that is our answer. So even though it did not exist beforehand, it exists now, and you're going to be tested on this, so you have to understand what to do in these circumstances. So now for our final topic today, we're going to learn the limits, taking the limits of piecewise functions. So if we have a super complex piecewise function f of x, and we're going to make this equal to 1 over x plus 2 when x is less than negative 2. We're going to have an x squared minus 5 when negative 2 is less than x is less than or equal to 3. And then lastly, this is going to be root x plus 13 when x is greater than 3. And our graph is going to be something weird looking like this. We're going to have a asymptote, and then it's going to be something here, it comes down to here, and then it's going to go up a bit, and then right here, there's actually going to be a hole. So what do we make of this huge random function? We're going to do 3 little parts here. The limit as x goes to negative 2 of f of x. What's it going to be? Well, just looking at the graph, negative 1, you would think. But since this is a vertical asymptote, nothing can ever reach there or touch it and ever cross through it. So this does not exist looking at the graph. But how are we going to solve this by looking at this huge piecewise function? The answer is simple. We're going to look at the domains and see what we can plug into based on the domain. So if we have an x equals negative 2, where can x equal negative 2 on this graph? Nowhere. So, since there's not an equals to or an equals to, negative 2 can never be plugged in. So this is simply does not exist for our answer. But what if we have something like this? Limit as x goes to 0 of f of x. Sorry, it's kind of sloppy. What's this going to be? Well, let's just disregard our graph for now. As x goes to 0, where does this included in our domain? Right here. We can plug in a 0 there, that's fine. So let's plug it in. Lim of x goes to 0 of x squared minus 5, but we're going to plug in a 0, so it's going to be 0 squared minus 5, which just becomes a negative 5. So that's how you compute a limit into a piecewise function without this graph here. And it makes it much easier to solve because then you know the domain that you can actually plug it into, and you're going to get an answer from that. And since none of these are necessarily double-sided limits, except this here, which we'll solve in a minute, we need domain restrictions for our limits to exist. Okay, so now let's do part C. This is going to be our last problem for today. What is the limit as x goes to 3 of f of x what's this going to be? Where's 3 included into our domain? Ah, the same place right here. So we're going to plug in our 3 to the x squared minus 5 function. So this is going to be the same thing, limit x goes to 3. This time it's going to be x squared minus 5. And if we plug this in, it's going to be 3 squared minus 5, which equals 4. So therefore our answer is 4 for this function. So that's how you plug in and solve the limits of a piecewise function like this, a huge, nasty little thing. And this is how you can compute limits in 4 different scenarios: the limits of piecewise functions, simplifying limits via the conjugate theorem, evaluating one or two-sided limits, and the basics of computing limits and applying it to the past 3 that we just learned. Thank you guys for watching. Make sure to like, subscribe if you found this helpful, and follow me on my journey to becoming a math tutor and to tutor people who are struggling in calculus. Thank you guys for watching. Till next time, bye.